And welcome back to another video. So we are starting our last course objective on flow in aquifers. So in this first lecture, we will talk about confined aquifers, and then in the next lecture, we'll talk about unconfined aquifers. And in the third lecture, the following lecture, we will study cases where there is recharge, so rain basically. So what happens when there's rain. So for now, for today, we're doing the simplest case, which is kind of a confined aquifer with nothing else going on. You can see here on the top right that for the unconfined aquifer that we'll do in the next lecture, the water table, the fact that there is a water table means that, you know, the flow is different. Well, the flow is conserved, but the water table level changes. In a confined aquifer, as we've said before, the thickness never changes, so it becomes a constant. So in the math, it's a lot easier to tackle. So let's see this. So you can see on this slide that the discharge, of course, is the Darcy flux times the area of the aquifer. Now, what is this area? It is illustrated here on the bottom left. So it is the thickness of the aquifer, again, a constant for a confined aquifer, times the width. So, you know, the depth inside the page here, or inside the slide, W. So B times W is the area in the page. And again, the aquifer discharge, Q, right, is this way. So this is the discharge flowing out of that aquifer. You can see here that we have two heads. So if we have two piezometers, right, two holes in the ground that tells us where the water level is, right, the head in the first piezometer, H1 is here and H2 is here. Remember, this is a confined aquifer, so our, you know, the water rises in those piezometers to give us the potentiometric head. Okay, and of course the decrease is linear because it's a confined case, right, so there's a linear decrease between the two. Okay, so we have everything we need. We have the area defined. Of course, Q is the Darcy's law, so it's K dH dx. And now we can derive the equations we want. Okay, so if we normalize the discharge by the width, right, we get that Q prime, which is Q over W, which is the Darcy flux times the depth, okay? So that means we're going to get flow, right, Q, but in units of cubic meters per second per kilometers of aquifer, right? So it's a per width of aquifer, per, you know, mile of aquifer. So we'll get some discharge, but normalized by width, right, per kilometer of aquifer. So this is what I'm restating here, right? So you can see the units. If we take the units of Q prime, right, it's in length cube per time. So let's say cubic meters per day, or, you know, million gallons per day, or whatever units you want to put, per length of width, right, length of that W unit. So if there's a river, for example, that can be per kilometer of river, right? Imagine there's a river going across the page here, right, draining that aquifer, or that aquifer draining into that river. That would be, you know, the recharge of the river, or the discharge of the aquifer into the river per kilometer of river, right? So let's say it's 1,000,000 cubic meters per day per river mile, okay? So just to set that up, because we're using this Q prime a lot in the following derivations. Okay, so let's say you have a new property and you'd like to know where the water would rise, right? Let's say you have a new property and you want to put a well, right? And you don't know what the stable level in that well would be. So, well, maybe you want to calculate that. This is what these equations we're deriving now can be used for. Okay, so as we said before, we know that Q prime is, you know, the hydraulic conductivity K times the depth of the aquifer, again a constant for a confined aquifer, times the head gradient, dH dx. Okay, well, now we can separate the variables, integrate on both sides. So separate the variables right here. So put dH on one side, dx on the other side. Everything else is basically some constants, right? So we can just throw them together. So Q prime divided by KB. We put dx on the left-hand side, and now we integrate both sides. Of course, the integral of dx is x, integral of dH is h. So that gives us a pretty simple equation, right? So x between 0 and x, so at 0 is just 0, so we don't count it. And then h between, you know, h0 and h1, or whatever the boundaries are. So that gives us h of x equals the initial, h minus q prime over kb x. Okay, so a pretty simple equation. Now we can calculate the head anywhere, right, between the two wells. So for example, if a confined aquifer is 33 meters thick and 7 kilometers wide, right, two observation wells are located 1.2 kilometers apart in the direction of the flow. The head in a well is 97.5 and in another is 89, right, where the hydraulic conductivity is given at 1.2 meters per day. That's a pretty standard number for hydraulic conductivity. Again, remember, a meter per day is good approximation. What is the total daily flow of water through the aquifer? So that gives us, how much water flows through the aquifer. What is the elevation of the potentiometric surface at a point located 0.3 kilometers from the first well and 0.9 from the second one? So let's say this is where you're thinking of putting a well, right, for your property. Well, what is the stable level in that well? Well, you can just plug these numbers, right, in those equations that I just gave you. So Q, the total discharge, that's the question, right? Not Q prime, now Q. So you have to multiply by the width, which is given, but it's still our same equation, right? It's Darcy flow times the depth, right? And then you plug in all those numbers and you find that this is an aquifer that gives you 2,000 cubic meters per day. Just as a reminder, this is in your books, right? So this is in chapter 4 in Fetter. So this is actually an example from the book. And you can find all this information, of course, in your book. What is the elevation? So again, now we have the h of x equation that we just derived. You just plug in the numbers again. Note that Fetter calls what I call Q prime, he calls Q prime, little q, right? So this little q here is my big Q prime. But this is the same equation, plug in the numbers and find that the head, or the stable level, if you will, in that piezometer, in that well, would be 95.3 meters. Okay, hopefully that explains a little bit what, flows out of a confined aquifer and how we can calculate those things. So those same approaches of, writing the equation for Q prime, using Darcy's law, and then deriving, the equations of motion will apply to an unconfined case that's a little bit more complicated in the next lecture. Thank you.